We are continuing class 12 physics, chapter 2, electrostatic potential and capacitance. In this video, we will discuss electrostatic potential due to an electric dipole at a random point. We will derive an equation for the same. We will also see the contrasting features of electric potential due to point charge and an electric dipole. Watch the video completely so that you get all points cleared, and if you think the video is useful, like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and press the bell button and all button for notification of more videos like this. Thank you very much. Come, let us start the class. We have to derive an equation for calculating potential due to electric dipole. Under this topic, we have to make 4 derivations. First one, potential at a random point, that is at any point. Second one, at a point on the equatorial line. Third one, at a point on the axial line along the dipole moment. Fourth one, at a point on the axial line against the dipole moment. We will derive an equation for electrostatic potential due to an electric dipole at any point, that is at a random point. Then apply that to the other 3 positions. Now the diagram to support the derivation. Electric dipole consists of a system of 2 equal but opposite charges separated by a very small distance represented as 2a. The 2 ends of this distance may be marked as B and C. Then BC is equal to 2a. The dipole moment P of this electric dipole is from negative q to positive q. It is a vector quantity. In the diagram, I have represented it as a red arrow. O is the midpoint of the axis of the dipole. For any calculations associated with the dipole, we consider the midpoint O. It is the origin. Now, BO is equal to OC is equal to 2A by 2, that is equal to A. What is the magnitude of the electric dipole moment P? That is equal to 2QA. Actually, it is Q2A, but it is always represented as 2QA. You have learned electric dipole in the previous chapter. Let T be the point where we want to find the electric potential. The distance of this point from the origin is taken as R, and it is much greater than the distance 2a. This is the position vector of T from O. This is the direction of the dipole moment, and this is the direction of the position vector. Electric field due to a dipole depends not only on the distance of that point from the midpoint of the electric dipole, but it also depends upon the angle between the dipole moment and the position vector at point O. Electric potential at a point is due to the electric field. Let me note the position vector R. 2a is much smaller than R. That is, the magnitude of R is much greater when compared with the distance BC, that is 2a. Angle between P and position vector R is theta. Electric potential at T will be equal to the sum of electric potential due to negative Q and positive Q. We have to find the total by using the principle of superposition, that is vector addition. Let R1 be the distance of negative Q from the point T and R2 the distance of positive Q from T. So potential at T, Vt is equal to V due to negative Q plus V due to positive Q. We already know potential at a distance R is equal to Kq by R. This is for a point charge. K is the constant equal to 1 by 4 pi epsilon naught. For negative Q, it will be negative Kq by R1. So potential at T will be equal to negative Kq by R1 plus kq by r2. So we have to get the value of r1 and r2. We have the value of r. We have to calculate r1 and r2 with reference to r. We use a simple principle in geometry. When a long line and a short line are at a very small angle and we have the magnitude of the long line, then we can find the magnitude of the short line. For that, we draw a perpendicular to the long line from the free end of the short line. AB is the long line. Then the perpendicular meets line AB at C. Then distance AC is the length of the short line and AC is equal to AB minus CB. What are the conditions? One line should be long, the other line should be short, and they should be at a very small angle. We can apply the same principle here also. In the diagram, I have shown BC a little long so that the diagram is very clear. We have already seen that 2A is much smaller than R. That is, R is much longer than 2A. We find that R2 is smaller than R. We can draw a perpendicular to R from the free end of R2, that is from C over to R. This perpendicular crosses line R at point D. The magnitude of R2 will be equal to TD. That will be equal to R minus the small distance OD. So we have the value of R2 equal to R minus OD. We will use a little bit of geometry again to get the value of OD. Consider the right angle triangle DCO. Base upon hypotenuse is equal to cos theta. OD is the base and OC is the hypotenuse equal to A. So OD will be equal to A cos theta. I hope you were able to understand these points clearly. Now substitute this value over the previous equation. R2 is equal to R minus OD. So the equation becomes R2 is equal to R minus A cos theta. Now we will find the value of R1. R1 seems to be longer than R. So we extend R downward, that is outward, that is beyond O. So the extended line becomes longer than R1. Now draw a perpendicular to this extended line from the free end of R1. The perpendicular is at point M on the extended line. Consider the right angled triangle BOM. OM is the base and OB is the hypotenuse. Angle BOM is theta because it is opposite to angle DOC. OM by OB is equal to OM by A because OB is equal to A. It becomes equal to cos theta. So OM is equal to A cos theta. You get the value of OM. R1 is equal to TM equal to R plus OM. Substituting for OM, you get R1 is equal to R plus A cos theta. We will rearrange the above equation as KQ by R2 minus KQ by R1 so that we take the positive value first and then the negative. Substituting for R1 and R2, potential at T is equal to KQ by R minus A cos theta minus KQ by R plus A cos theta. KQ is common, therefore it can be taken out. Then it becomes KQ into 1 by R minus A cos theta minus 1 by R plus A cos theta. When you solve this, R plus A cos theta minus R minus A cos theta. In the denominator, R minus A cos theta into R plus A cos theta becomes R square minus A square cos square theta. Positive R and minus R in the numerator get cancelled, and what remains is A cos theta plus A cos theta equal to KQ 2A cos theta. In the denominator, we know that the value of A is very, very small, because 2a itself is very small. So a square becomes further small, and a square cos square theta is very small. So it can be simply neglected. R square minus a square cos square theta can be taken as r square in the denominator. So for potential at T, Vt, the equation becomes kq into 2a cos theta by r square. Q 2a is equal to 2qa, which is nothing but the dipole moment P. So electric potential due to dipole becomes equal to Vt is equal to K P cos theta by r square. This is in terms of dipole moment. So we have derived an equation for calculating potential due to dipole at any point in the electric field of the dipole. You may be asked to give the vector form of this formula. It is very easy because cos theta is associated with dot product. So the equation will be Vt is equal to Kp dot r cap by r square. R cap is the unit vector. Remember the condition, R is much greater than A. Applying the formula, we can see that in the equatorial plane of the electric dipole, the electric potential will be 0, because the angle between the dipole moment P and the position vector R will be 90 degrees, and cos 90 is equal to 0. Potential at a point on the axis of the electric dipole lying parallel or along the dipole moment will be equal to Kp by r square, because the angle between the dipole moment and position vector will be equal to 0, and cos 0 will be equal to 1. So you get a positive value. Similarly, electric potential at a point in the axial plane against dipole moment will be equal to negative Kp by r square, because the angle between the position vector and dipole moment will be equal to 180 degrees, and cos 180 degrees is negative 1. So you get a negative value. Now we will see the contrasting features of the electric potential due to point charge and an electric dipole. For a point charge, electric potential depends only on R, that is the distance of the point from the charge. But for an electric dipole, it depends upon the position vector R and the dipole moment, and also the angle between dipole moment and position vector. Another contrasting feature is that electric potential for a point charge is directly proportional to 1 by R, whereas for an electric dipole it is directly proportional to 1 by R square. That means for the same increase in distance of the point from the point charge or from the midpoint of the electric dipole, the decrease in potential will be much less for the electric dipole than for the point charge. Such questions are asked for the examination. Okay. If the video was useful, like the video, share the video, and also leave your feedbacks as comments. If you have not yet subscribed, subscribe, press the bell button and all button for notification of more videos like this. Thank you very much. We will meet in the next video with the next derivation. Thank you. Till then, bye. Take care.